Now we'll discuss the procedure in the case 1, that is the shear in weld from in-plane torsion. So we have the force F is in the same plane as the weld group. Consider here we have a fillet weld on the top and bottom. So in this case the force F is in the same plane as the weld group. This one is called as weld group. So if you look this figure from this side, you will get a front view. This one is representing the top weld and this one is representing the bottom weld. This one is plate A, that is a gusset plate, and this one is plate B, which is welded, and the force is acting in the same plane as the weld group. Let here the length of each weld, top and bottom, is equal to D. Here this side is equal to H actually, but we'll show here this equal to T. The step number 1 is to locate the centroid. Now these two are the similar rectangles, so just by observation we can locate here centroid. So let here point O represent here the centroid. So you have to complete the first step number 1, that is the location of the centroid. Second step is to measure the distance between the centroid of the weld group and the line of action of the force. So here draw vertical line because line of action is vertical, and measure the distance between the centroid of the weld group and the line of action of force. This one is eccentricity equal to E. Then we can shift the force to the point O and we can observe the effect. Whenever the line of action of the force is changed, then the force will be shown as it is plus one additional moment is generated. This time the additional moment, that is the twisting moment, is generated about the point O, that is same as equal to F into E. So if the line of action of the force will change, the force will be represented as it is. Plus one clockwise turning moment is generated about the point O, and this clockwise moment will be equal to torque T is same as equal to F multiplied by E. And this is resisted by the weld group on the top and the bottom. Now we'll see the effect of F and the effect of torsion independently on the same weld group. Now it is not compulsory here that the centroid always lie at the symmetry axis. It depends what type of weld you will do. Suppose you are doing the welding like this one, then your centroid will be somewhere on this side. So you can calculate the centroid by dividing the standard rectangle that I already discussed to you. We have this rectangle equal to 1. Then we have second rectangle, and then again we can divide here third rectangle, and then you can use the formula to find out x bar as summation of ai xi divided by summation of the ai. Similarly we can calculate y bar is equal to summation of ai yi divided by summation of ai. So this is a procedure to find out the centroid if you are given the welding type is different type here. But as far as we are considered right now here, we have the top and bottom and both are symmetrical. So exactly at the vertical symmetry axis we have centroid location equal to point O. So this vertical force is opposed by the area on the top and bottom, and it has a shear force equal to V. Here V represent the shear force, and the value of the shear force V is same as equal to F. This time the total area on the top and bottom is equal to 2 times the throat thickness multiplied by D, where D is the weld length. The weld length on the top and bottom is same. So we have 2 times of T multiplied by D, and it will create a shear. This time we will call it as a primary shear. So we have primary shear, which will represent as tau prime, will be equal to the shear force V divided by area A is same as equal to the force F divided by total area is 2 times the throat thickness multiplied by the length of weld D. Throat we can replace as 0.707 times the leg size. The value of the shear stress is uniformly distributed over the entire weld group. That is, you can take any point, either this point or this point or this point or this point, everywhere the values remain same. That equal to tau prime. This one is also equal to tau prime. At any point you can take, this is uniform, is equal to tau prime. So this one is the effect of the shear force F. Now we'll discuss the effect of the torque. We know that the torsion formula we have T by J is same as equal to tau divided by R. And we are interested in the maximum value. So this time we'll represent the tau as equal to tau double prime. And this value of tau double prime will be equal to T multiplied by R divided by J. So naturally in this case, if we are interested in the higher value of tau, then the radius should be higher. And if you see this figure from the center of gravity, this point has a higher value of radius, or this point has a higher value of radius, or this point is a higher value of radius, or this point is a higher value of radius. Other point inside has a lower value of radius. So at this point we'll show the effect of torque. For this one I have slightly increased the space here. This one is the same as our center O. This one is the critical point here because this point is the farthest and the value of R will be higher value. So this point is called as the critical point. This value of R is same for all the point because our figure is symmetrical. Our torque is acting in a clockwise sense, that is the external torque acting is equal to T. So you have to show the direction of the shear in the same sense as the torque. Here tau double prime is perpendicular to the line of joining the critical point and the centroid of the weld system O. And this one is representing the tau double prime. Here R represents the distance of the corner point from the centroid of the weld group. I will show at one point here only. Other value will be remain same here. The direction you have to just maintain as the same as the external torque. So two stresses are acting here. One is the tau prime and second is tau double prime. The secondary shear stress is due to the torque T, which is given as F into E. Secondly, we have shear stress, that is the secondary shear stress is directly proportional to radial distance R, and therefore we have to select the critical point. So this point here is called as critical point because for this point we have the radial distance is maximum. And the geometric relation between the tau prime and the R is that they are perpendicular to each other. Not only they should be perpendicular, but you have to select the proper direction. The direction should be such that the torque developed by tau prime must equal to the external torque equal to T. Don't show the arrow in this direction. So two stresses are produced. One is tau prime, which one is called as primary shear due to the force F, and secondary shear due to the torque T, which is given as F into E. Once we find out the primary shear tau prime and secondary shear tau double prime, then we have to calculate the resultant shear stress, that is equal to tau, which is equal to the vector sum of tau prime plus tau double prime. Tau prime is acting vertically downward, so you have to show it vertically downward. On the tip of this you have to show the tau double prime. So here you have to represent the tau double prime, and then you have to join the first point with the last point, and you can calculate here the value of tau. But for calculation purpose you have to always use the absolute value, that is the positive value of the shear stress. Step number 1 is to calculate the tau prime. Second step is to calculate the torque, which is F into E. Since here the shear stress is directly proportional to R, so you find out the furthest distance, that is this is a critical point. At critical point you have to show the shear stress in the same direction as the torque. Then you have to do the vector sum to find out the resultant shear stress tau. You have to just vectorically add tau prime and tau double prime, and you have to take the absolute value. Up till now I hope the steps are clear. Now we'll discuss here procedure how to calculate resultant value of the tau, that we can use the triangle law and you can find out the value of tau prime. Second procedure is that we can resolve the tau prime into two values. One is horizontal component and the vertical component. Vertical component of the tau prime will be added to tau prime and the horizontal component will be added. And then since here the two components are perpendicular, we can use the Pythagoras to find out the resultant value of tau. So that procedure we are going to discuss now. So we'll continue our discussion for this type of weld group to resolve the value of tau prime into two components, one horizontal and vertical. In this case we have tau prime is equal to torque which is F into E multiplied by R divided by J. How to calculate value of J? Already we are knowing it. So we'll resolve this tau into two components. One is horizontal component that will be called as tau double prime, is acting along the x direction. So it is tau double prime x. And second component is tau double prime, is acting along the y direction, which one is same as the direction of the primary shear stress. Now this makes a sense here because we can very quickly calculate the value of tau double prime x, and we can add here tau prime and tau double prime. So this one is a very simple procedure to calculate the value of resultant shear stress. So if I show here the tau double prime x, horizontally tau double prime y, and on the tip of this will show tau prime. So this one is representing the primary shear stress. Join the first point with the last point and we'll get the resultant value of the shear stress. So this length of arrow represents the resultant shear stress, and our resultant shear stress can be obtained by Pythagoras. So we have under root of tau double x prime square. So we have tau double prime square plus these two vectors can be added is tau prime plus tau double prime y, and then you have to make a square. In this fashion we can calculate the absolute value of the tau. You have to take the positive value here. Now the question comes here, how we going to calculate tau double prime x and tau double prime y. Now we know that the tau double prime is given as t multiplied by r by j. So using this concept we can calculate tau double prime x and tau double prime y. Now check here the procedure to calculate the value of tau double prime x. This value is horizontal and we need to calculate this value here. So this one is tau double prime x. The two welds are separated by distance equal to b. So the top weld from point O, that is the centroid of the weld group system, will be equal to b by 2. So vertical distance between the point O and O prime will be equal to b by 2. As per the definition here, we have to take the perpendicular on the line of action of tau double prime. So we'll extend this line. This line will pass through now CG of the top weld, and we have to take this perpendicular distance. So this will be the value of R will be equal to b by 2. In that case we can calculate tau double prime x using the same formula of a torsion T. So this is T multiplied by b by 2, where b by 2 is our R, divided by J, where J is the polar moment of inertia of the weld group. Similarly, we can calculate tau y double prime. So this time we require this distance. This distance is same as the half of the length weld. We have taken this weld length equal to d. So this value is same as equal to d by 2. And this one is the shortest distance. So this will be the ry value. I will call this one as rx value. So we can calculate tau double prime. So we have tau double prime y will be same formula again, torque multiplied by r. So this time we have to use the value of ry. So we have torque multiplied by distance equal to d by 2, that is the radial distance equal to d by 2 divided by the polar moment of inertia. In this fashion we can calculate tau double x prime as t multiplied by b by 2. b by 2 is the vertical distance between O and O prime, and tau double prime y we can calculate torque multiplied by d by 2 divided by polar moment of inertia j. So independently calculate here the value of tau double prime x and tau double prime y. Use this vector diagram, calculate the final value of tau, that is the resultant shear stress. A steel bar of thickness h is equal to 5 mm to be used as a beam is welded to a vertical support by two fillet weld as shown in the figure. Find the safe bending force F if the allowable shear stress in the weld is equal to 140 megapascal. So we have to find out here the force. We have two fillet weld. So this one is the case when the plane of the welded joint and the force is in the same plane. That is the case number 1. Because of this, the stresses developed will be the primary shear stress due to the force F, and one is the secondary shear stress due to the torsion T. For this one, first you have to find out where is the centroid. Centroid due to the symmetrical loading will be the symmetry axis. So this one is a two symmetry axis. These two symmetry axes meet at a point here that equal to the centroid of a system. And this distance is same as equal to 25 mm. So distance between the weld group centroid and the line of action of force is called as eccentricity E. This value of E is same as equal to 150 plus 25. So we have eccentricity is equal to 150 plus 25, that equal to 175 mm. We have shear force is same as equal to force F. We'll take this value in kilonewton. And we have torque T is equal to force multiplied by E. This will be kilonewton mm. So we have E is equal to 175. So we have torque is equal to 175 times F kilonewton mm. We want to calculate here the polar moment of inertia J. So these are the two parallel welds here of weld length equal to D and the separation distance that is equal to B. In this case, we have the total polar moment of inertia is T multiplied by D multiplied by 3B square plus D square by 6. Whether we have this position or the position is changed by right angle, value of J is remains same. So you have to use this value of J. So we have length of weld is equal to D is equal to 50 mm and the distance of separation equal to B is equal to 50 mm. T we can replace as 0.707 times of H, and he has given the thickness of the plate equal to 5 mm. So you have to use the value of H is equal to 5 mm. So let's calculate here J first, then we'll calculate the secondary shear stress using the torque. So total polar moment of inertia is T is 0.707 multiplied by H, which is equal to 5. So in this case the throat is replaced as 0.707 multiplied by H multiplied by D value that equal to 50 into 3 times B square is also equal to 50. So we have 3 times 50 square plus we have D square is 50 square divided by 6. So we have total polar moment of inertia is come out to be 296.41 into 10 to the power 3 is mm to the power 4. Secondly, we have cross section area which is resisting the weld will be 2 times of throat multiplied by the length of weld equal to D. That is we have 2 times of 0.707 times H multiplied by D. That is we have 2 times of 0.707. We have H is equal to 5 mm and D is equal to 50 mm. So we have resisting area is equal to 353.5. That will be mm square. Here the force F will develop a shear stress that equal to tau primary, and we have tau primary will be equal to same as V divided by A. In this case we have V is equal to same as equal to F. You have to use that value in kilonewton. So we have F into 10 to the power 3 because we are use kilonewton divided by area is 353.5. So we have shear stress come out to be 2.829 times F. Remember here the value of F we are using as kilonewton. So this one is the top weld, this one is the bottom weld. The length of weld is equal to D is equal to 50 mm. This one is the position of centroid and this one is the centroid of the top weld. First we have calculated here tau prime, which one is acting vertically downward, is 2.829 times F. So tau prime is acting vertically downward. Then we can calculate the value of tau x and value of tau y. We have tau double prime x and we have tau double prime y. For tau double prime x, we have radial distance is this distance. That is same as equal to Rx, and this distance is same as this distance, which is equal to B by 2, which is equal to 25. Similarly, for tau y prime, we have perpendicular distance is this distance. We call this distance as ry, and this distance is same as d by 2 is again equal to 25 mm. So this time rx and ry is same value. So we have rx is same as equal to ry, and we know the shear stress tau x double prime is same as equal to torque multiplied by rx divided by polar moment of inertia j. And since here rx value and ry value is same, j is same, the value of torque is also remains same. So we have tau x double prime is same as equal to tau y double prime. So let's calculate here tau x double prime, which is same as equal to tau y prime, that is double prime, is equal to torque. We have torque is equal to 175 kilonewton. So we have 175 kilonewton is 10 to the power 3. Value of Rx is equal to 25 divided by J, that is a polar moment of inertia, which one is 296.41 into 10 to the power 3. 296.41 into 10 to the power 3. And this value is same as the tau double prime y also. So in this case we will get tau x double prime is same as equal to tau y double prime, and we have this value is equal to 14.85 times of f. The permissible value of the shear stress is 140, so we have tau max will be equal to, the resultant shear stress is under root of tau x prime square tau x double prime square plus we have tau double prime y plus tau prime and whole square, and you have to take the under root and you have to solve this. Out of that we have tau max is equal to 140, so we have 140 equal to under root of, we have tau double x prime is equal to 14.85 square, 14.85 f square of it, plus tau y double prime is also same value 14.85 times f, plus we have tau prime is 2.829, so we have 2.829 and you have to take a square. Solve this, you will get the required force F. So in this case we have force F will be equal to 6.06. This answer will directly come in kilonewton because we have assumed the shear force is in kilonewton. So finally we are getting the shear force equal to 6.06 kilonewton. This theory already I have discussed you how to find out the value of tau x double prime, tau double prime y and tau prime. Tau prime is same as V by A, and to calculate the tau x prime and tau y prime you have to use the torsion formula. For that you require the radius. So for tau x double prime the radius will be equal to B by 2, and for tau y prime the radius will be equal to 25. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.